Sophie, Caden, and Sophie's online?
Yeah, she said she's sick,
Okay.
so she was hoping.
Yes, that is fine. So they are there. Right. Okay, so as I said, I have not graded the test yet. I have a couple people that need to make them up. Reminder, you had Prepare to Learn that was due last night. So if you haven't done it, get that done. Your vocab is due on Sunday. We're going to start doing some calculations with light. And so there's an active assignment on that that is due on Sunday as well. So those are things to look forward to. We have 4 remaining class days. So I'm hoping to go over your exam on the Monday, on next Monday. But we also have to cover some material on electronic structure because the following Monday we have a quiz. So quiz 6, the only time to take the quiz is that Monday in class. If you can't be in class that day, that will be your dropped quiz. So if you have some other quiz you would like to drop, be in class that Monday. Because I have to get that quiz back to you on the last day of class. And so I don't have the opportunity to allow people to make it up at a different time. Questions? Okay, so we're gonna dive right in with, when is this following me? Oh, good. I got it to stop following me. I'm so happy. Light. I did post this on Facebook, not Facebook. Post anything on Facebook. I posted it on Canvas. And so I'm going to go kind of quickly through it. But if you need to look at the pictures in more detail, then you can look at those pictures on the slideshow on Canvas. Come on, there's my cursor. Oh, this was doing this the other day too. Give me my cursor back. No, I guess it'll just record like that. Okay. I'm also going to hand out to you a paper that has the problems we're working on it, so you don't have to spend time rewriting those problems. Okay, so this chapter is about electronic structure, but we start talking about light. Why? Well, some important things to know. Light acts both as a wave and a particle. You may have heard of this before. It's called wave-particle duality. The particle version of light is called a photon. We can, for the waves, calculate the wavelength, energy, and frequency, and we'll do so. It is important for chemistry because it's used to probe chemicals. So we have all kinds of spectroscopy where basically we shine various kinds of lights on chemicals, see what's absorbed, what's reflected, that kind of thing. And that tells us about what's going on in there. But what's most important for the electronic structure is that atoms can emit light, and depending on the energy of the light that is emitted, that tells us something about the electronic structure. That's kind of where we're going with all of this. So first we have to figure out how are we going to do the calculations, and then in the next section, we're going to relate those calculations back to the energy levels in an atom. All right, so waves have different things we can measure. One we won't worry too much about is the amplitude. So you can see the arrows there going up and down that tell you how high the wave is. And for light, we don't worry about that too much. But that is one thing that's in there. We can kind of think of that as being the intensity of it. So a sound with a greater amplitude would be a louder sound. And light with a greater amplitude usually has more photons. So that's why we don't usually work with the amplitude. What we will care about is the wavelength. You need to keep track of the symbols we use for these because we use Greek letters. So wavelength is used for all kinds of light, but when we talk about visible light, we usually associate the wavelength with the color. So longer wavelengths will be more red, shorter wavelengths will be more purple. So how do we measure wavelength? If you look at the bottom of the screen there, you can see it's measured from the lowest point of one wave to the lowest point of the next wave, but really it can be from any point on the wave to the same point on the next wave. What we usually do is either do the peaks or the troughs, so the highest points or the lowest points, because every place else there are two of those points on the same wave, and we don't want to get confused by, say, picking a point that is in the middle of the upswing and then going to the middle of the downswing and thinking it's the same thing. That's not the same thing. So either do the peaks or the troughs. So that's our wavelength. Sometimes what I might do is give you a scale on a graph like this that maybe all the way across is say 12, and ask you what the wavelength is. And so since there are two waves are 12, one wave is 6, and you would tell me it's 6 of whatever unit that was measured. All right, other things we measure are the frequency. Now the frequency isn't a physical aspect of what we look at on the wave. It's not a distance, but it's rather a speed or a rate. And so it is just per second or cycles per second. So what we have to imagine is if these two waves went across the screen in 1 second, that would be 2 waves per second. And so that would be our frequency. And if those went across in a microsecond, then we would have to have a much smaller unit, or I'm sorry, many more waves going across in 1 second. So micro is the little version of a million. So it would be 2 million waves per second. So we'll show you how to calculate that in just a minute. So for wavelength, we use the Greek letter lambda. It's lowercase, so you may have seen lambda as just kind of an upside down V in the capital letter form. Some of our Greek societies use a lambda. In the lowercase, it kind of looks like an upside down Y. So that is L for length. And frequency is the Greek letter nu, which very conveniently looks like a V, which totally makes sense. So some people just call it a V. If you want to call it a V in your head, that's fine. But if you hear me saying nu, it's because that's the Greek letter nu, which is the lowercase n in Greek. All right, so C equal lambda nu. C is the speed of light. And in a vacuum, all light travels at the same speed. So C is considered to be a constant. Ooh, grab this. And if you don't have one, a calculator. The air on the earth, we approximate as a vacuum. So even though the air does slow down light a teeny tiny bit, it's way out past the sig figs that we usually use for the speed of light. And so we just assume it's traveling at that same speed. Okay, but key point is that all light travels at this speed. And that is the fastest speed that we are aware of. So the speed of light is the speed limit. Nothing can travel faster than light. Okay, so if we want to calculate the frequency, we just rearrange that equation and solve for nu, which remember is the V looking thing. And that is going to give us the frequency. Fortunately, it looks the same. If we do lambda, we just swap those two variables. So if you mix up what the variables mean, you're still going to do the right calculation. C divided by the number you have. Okay, so when we compare things that have different wavelengths, since they are all traveling at the same speed, the speed is measuring, say, the top of one peak, that particular peak, how fast is that going? In comparison to the frequency, which, yes.
C, speed of light.
Speed of light, yes. So the frequency is measuring how many times up and down per second. The C is measuring how far does one particular wave go distance-wise. So it's in meters per second. And so this picture is particularly done to show how visible light works. where red are the longest wavelengths. So you can see up there that those are definitely longer than the ones below. And the blue or purple end is the shortest wavelengths. If all of that is traveling the same distance in the same amount of time, then we can say, okay, A has a lower frequency. Fewer of those waves are going by each second than are going by for the blue ones, which are going, there's a ton of them going by per second. But we can also say that any particular one of those waves is still just taking 1 second to cross from one side to the other. So even though more waves go by, each wave is moving at the same speed. Okay. All right. There are lots of different kinds of light. We normally think of light as visible light, but light to a chemist is any kind of electromagnetic radiation. We sometimes call EM radiation. We'll talk about what that means in a minute. But this kind of shows the range of things that we really examine. So on the low frequency end, with very long wavelengths, we have radio waves, and television waves, when they used to be sent out analog, would also be in that category. Okay. And so the frequency, that the number that you tune your dial to on the radio, would be in kilohertz. How many kilohertz? How many kilohertz the frequency of that radio station was. In the middle, we kind of have microwaves, microwave ovens in the US. Whatever organization controls these things limits it to a particular frequency. So other microwave frequencies can be used for government purposes or scientific purposes or whatever. So most microwaves tend to have the same frequency. And then we have infrared. And then notice visible is very narrow compared to all the others. Then we have ultraviolet, X-ray, and gamma ray. So a question I sometimes ask is, put in order the 7 different kinds of light. So you need to know from low frequency to high frequency, or from long wavelength to low wavelength, what those are. All right. So X-rays and gamma rays are the ones that we call ionizing radiation. Those are the damaging ones. And so they're the high energy, high frequency ones, and they have teeny tiny wavelengths. If you remember the order of the rainbow, if somebody taught that to you at some point, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Ultraviolet means higher than violet, so it is higher frequency than violet. So it sits right next to the visible light, right next to the violet side. And infrared sits right next to the red side. So those you can usually get. They're right next to visible. Visible's in the middle. And then microwave and radio are on the lower ends. All right, so how long are these wavelengths? Radio waves are usually measured in meters, sometimes kilometers. So AM radio isn't used too much anymore. When I was growing up, it was about 40, 60. The advantage of AM radio was those big, long radio waves that could be a kilometer in length, could go long distances and could go over hills and things like that. But they were really susceptible to the weather and to things like bridges and things. So if you're driving your car and you go under a bridge, your radio cuts out until you get to the other side of the bridge. So the FM radio stations, theirs are more like a meter, 3 meters, something like that. The wavelength might be the length of this desk. And so if you go under the bridge, the radio waves go under the bridge with you, and you can keep listening to your radio. Microwaves tend to be on the order of centimeters. So a radio, or so the microwave oven is, if I remember correctly, about 7 centimeters for a wavelength. And And so the little holes that are in the door, if you have a door to your microwave, it's kind of darkened because there's like a screen with little holes. The screen itself would block the microwaves, and the holes are about 0.5 centimeter wide. And the thinking is that that's too small for the microwaves to get out because the microwaves are about 7 centimeters long. So it blocks the microwaves because they're smaller. Infrared light, we're looking at microns or micrometers. So this is 10 to the -6th. Now, when you're at the edge of the infrared that's right next to red, sometimes it gets measured the same way that visible light does. But usually when you see how long is the wavelength of IR, they're going to say it's this number of microns. For visible light, we usually put it in terms of nanometers, and it will be hundreds of nanometers. So the range for visible is about 700 to about 450 nanometers. The 700 end is the red end, and the 450 is the violet end. So I may give you a question that says, if I have a wavelength that is 650 nanometers, is that more likely red or green or violet? And you would say to yourself, well, 650 is pretty close to 700. It's probably still in that red range. All right. Ultraviolet is in the tens to hundreds of nanometers, and it goes right up to the edge of violet. So usually violet cuts off right around 450. Sometimes people will say closer to like 420 nanometers for violet. So I've just kind of said, well, 400 and below is definitely going to be ultraviolet. So I have a couple of lights. They're like little flashlights that have ultraviolet light that you can get things that like rocks that will glow under ultraviolet light. Those are sometimes called black lights. And one is at 395-ish nanometers, so just shy of 400, and one is like 360 nanometers. Okay, so that's your range for ultraviolet. So visible and ultraviolet are both measured in UV, or in nanometers rather. X-rays are measured sometimes in angstroms. I couldn't find the symbol for angstrom to put it on here. It looks like a capital letter A with a circle on top. And this is 10 to the -10, which to our brains that are used to using tens, that makes a lot of sense to use that one. And that's roughly the length of a bond between atoms. So that would seem like a typical thing to do. But in the metric system, when we go from meters to millimeters to micrometers to nanometers to picometers, we're going in sets of 3. So the picometer is going to be 10 to the -12, and the nanometer is 10 to the -9. So sometimes it's just reported in picometers. And then gamma rays would also be measured in picometers, but instead of being hundreds of picometers, it would be like tens or individual picometers. Or smaller, tenths of a picometer. All right, so those are our ranges. The ones we care about most right now in this class are going to be IR through UV. As you go on in chemistry, you'll talk about how we can use microwaves to understand how molecules rotate, and infrared to understand how molecules vibrate, and X-rays to understand crystal structures. But right now, we're just concerned with what's going on inside one atom and not whole molecules. So we will just focus our attention on IR through UV right now. Okay, so how do we do some calculations? This one's on your paper. A red laser pointer has a wavelength of 650 nanometers. See, I told you 650 was red. What is the frequency of this light? So what is the equation we're going to use? Well, so far we only have one equation, and that's our C equals lambda nu. And I'm just now realizing I haven't written down anywhere what C is, but it is at the top of your page. So if you only have 2 sig figs or 3 sig figs, like we have, this one's 2 up here, you can just round this to 3. But it's 2.998. times 10 to the 8th meters per second. So that's how fast it is going. All right. So we rearrange C equals lambda nu to solve for nu. So nu equals C over lambda. Right? C goes on top. So I've put the full 2.998. It's one of those things, once I know how something is, I have trouble going back to the hand waving approximation. And then we divide by the wavelength. Now notice this wavelength isn't in correct scientific notation. So correct scientific notation, we would have 6.5, but then that would change the -9 to -7. Your calculator will understand it if you put it in this way. So I recommend just leave it in the hundreds times 10 to the -9, and that way you don't accidentally shift it in the wrong direction. Remember you're dividing on the bottom by something that is times something else. So either put it in parentheses or you can do the thing on the bottom first and then divide those two numbers, or you can say divided by 650 divided by 10 to the -9. I highly recommend you practice these calculations so that you get used to how you work that exponent on the bottom. All right, so we got 10 to the 8th on top, 10 to the -9 on bottom. Of course, that's going to be shifted a little. So when we've got 10 to the negative something on the bottom, on the top, that would actually be 10 to the positive something. So we're going to get something that's 10 to the really big number. Okay. So I get 4.6 times 10 to the 14th. And the units, the meters would cancel and it would be 10 to the 14th per seconds. If you're like me, you don't like saying per without having something before the per. So we could also just call it hertz. So a hertz is the same thing as a per second. All right, so notice that I have 2 sig figs because the 650 only has 2 sig figs. Right, so feel like we can handle that? Okay, on your calculator, there are 2 basic ways to do scientific notation if you don't want to plug in times 10 to the every time. On smaller calculators, i.e. not graphing calculators, usually there's a button near the enter or the equals that says EXP. So EXP means times 10 to the. So the way that you would enter this would be 650, hit the EXP, and then -9. If you do that, then it already knows that whole thing is together and you don't have to worry about that. You're dividing by 2 different things. Now, if you have a graphing calculator, usually there is something that says capital letter EE. Don't use the lowercase e because that means something entirely different, but capital letter EE. Sometimes you have to hit shift to get to that one. And same thing, your calculator understands that's all one unit. If you would rather just stick to typing 10 to the, that's fine. All right, so most of the time for visible light, those frequencies are going to be 10 to the 14th. So I often give you questions where there's a color. And if you get a frequency that's 10 to the 14th, maybe 10 to the 15th, especially if it's purple or ultraviolet, that sounds good. If you are getting 10 to the negative something for your hertz, you probably did something wrong and you need to go back and check your work. Okay. Next one. I'm going to let you do this. It's the same type of calculation, just plug in different numbers. A green laser pointer has a wavelength of 520 nanometers. So what is the frequency of this light? So you're still going to do the same C, 2.998 times 10 to the 8th on top, and divide it by that 520 times 10 to the -9. So plug that in and see what you get. Yes.
What I would do is it's 520 divided by, so you have the E. So divided, that was supposed to be 2.998 EE 8. And so it's gonna look like that's the exponent, but really it's times 10 divided by 520. And then,
All right. So how many people think it's A? B, C, D. Very good. Okay, so even if you didn't have your calculator, if you were just paying attention to what I said on the last slide, that usually it's going to be times 10 to the 14th, that tells you what that answer is. So if you're doing a multiple choice test and you're like, I don't have time to do this calculation, that would be a good quick guess. Circle it so you can come back and actually do the calculation, but be like, oh, okay, it's probably that one because it's in the right ballpark. Okay, so these are the pictures that I'm like, if you need to redraw these pictures, worry about it later. So light has some different properties that show that it is a wave. So one thing that waves do is when they interact with one another, if two high points or peaks of the waves come together, they constructively interfere and the wave gets bigger. If you have a high point and a low point come together, a peak and a trough, they kind of cancel each other out. And so if we have light passing through slits, we get what is called a diffraction pattern of these light and dark spots. So the fact that light does this tells us it's a wave. So that's what that top thing says. Light diffracts, forms diffraction patterns. That tells us it's a wave. The other thing it does is it refracts, it bends, or not really bends, it changes direction when it hits water. So it immediately changes its speed. And instead of forming a curved path, it will just go in a straight line, hit the water, and then change its direction. Okay. Whereas if I'm throwing a pebble, it's going to try to keep the same path, but as it slows down, start to curve. Okay, and so we have evidence that light does this. The best evidence for this is that if you send light through a prism or like a crystal that has different angles of the edges, it will form a rainbow. So rainbows are evidence that light refracts. Okay, so all this is to say, yes, light is a wave. All right, light is electromagnetic radiation. That's that EM radiation that I was telling you about before. So this stands for electricity and magnetism. And so it turns out that basically anytime you have electricity moving as a wave, magnetism is going to be right there along with it. It's like its shadow that follows it around with each other. They run perpendicular to one another. So we have here the electric field is kind of tan colored going up and down, and the magnetic field is going perpendicular side to side. So this is how we can make an electromagnetic magnet. If you've ever done that experiment where you take a wire and you wrap it around a nail and you send a current through it, and then the nail can pick up stuff, we can use electricity to make a magnet. And this is also how power plants work. They take magnets and hand waving gesture kind of thing. They basically get the magnets spinning around electric wires, which causes electricity to start moving. So electricity and magnetism work hand in hand, and all light is a wave made of both of these things working together. And that is why we say radio waves and microwaves and X-rays are also light, even though we can't see them. So what calls it light is not the fact that it is visible to us, but the fact that it is traveling like this. All right, so here's our spectrum again, just so you can see that. So all radiant energy travels at the same speed. So that red light and that green light were both traveling at the speed of light, but radio waves travel at the speed of light. Gamma rays travel at the speed of light. So if you've ever been at a stadium or in a very large field when somebody's been talking on a microphone, the sound coming out of the speakers is traveling at the speed of sound, which is much slower than the speed of light. So if you've got a speaker on one side of you and a speaker on the other side of you, if they're far enough apart, you're going to hear a difference in the timing from them because that electricity is traveling through the wires to the speakers so that it's pretty consistently coming out at the same time. But if one speaker is much farther away from you than the other, there's a delay in the amount of time that that speaker comes to you, or that sound comes to you. All right, high frequency is associated with high energy. Okay, so far we've talked about frequency and we've talked about wavelength. Now we're going to talk about energy because energy is what is going to tie us back to those atoms. So that's what we're totally interested in. So that means that since wavelength and frequency are inversely proportional, one goes up, the other goes down, just like pressure and volume, wavelengths and energy are inversely proportional. Long wavelengths, which would be big, would be low energy, which would be small. And this is why X-rays are more damaging to you than radio waves. We got radio waves traveling through this all the time, but we wear lead vests to protect us from X-rays at the dentist office or if we break a leg or whatever. All right, so based on that, which of these colors of light from red through yellow down to purple, what color of light has the highest energy? Purple has the highest energy. So it's a little bit weird that we use red as hot water and blue as cold water when those colors actually energy-wise would be reversed. The blue is much higher energy than the red would be. All right. So a little bit of background. For a long time, Newton said light is a wave. People were like, yeah, Newton, he's a bright guy. Sure, he's right. Then the early 1900s, about 100 years ago, people start doing some experiments and are saying, wait a minute, there's a little bit of problem. I'm not going to have you explain these to you, but you'll hear this terminology or you'll see this terminology as you read through the chapter. So I just want to briefly cover it. So there are 3 problems with light being a wave. Light should not be quantized. It shouldn't come in individual pieces, right? If it's a wave, it's a wave. It's going up and down for as long as it can. So one problem is black body radiation. One problem is the photoelectric effect, and one problem is the atomic spectra. We'll talk about atomic spectra on Monday. So we're going to talk just a tiny bit about black body radiation and the photoelectric effect today, just to give you an idea of why we say light is a photon, a particle, in addition to it being a wave. All right. So black body radiation, what is it? It is basically the idea that when you heat something up enough, it starts to glow. So if you've seen a campfire as the light or as it's going out, even after the flames go away, you still see red embers. If you've had a stove that turns red or orange or yellow, it's getting hot and the coils or whatever it is the heating element is starts to change colors. We mostly have the fluorescent bulbs now, which work on a different principle, but the incandescent lights that we're phasing out, they have a piece of tungsten usually in them, a piece of metal in them that they're running electricity in there until it gets super hot and then it starts to glow. So I'm always impressed that that can happen so quickly. You flip on the light and it turns on. But there you go. So that is what black body radiation is. The reason that that's a problem is that if we were to be graphing the wavelength of the light and the intensity of the light, we would expect to see an ever increasing curve for that. And physics, hand waving, that doesn't happen. And the only reason that we can explain the observed curve, the green one that goes up and then comes down, is that if light can only be emitted at certain energies. Okay, so this is just kind of a trust me, the math works out but this is where we get this equation from, which is what we want to be looking at to figure out the energy. Okay, so the energy of one photon is a constant called h times nu. Nu, remember, is our frequency. So h is just a number I will always give you, and it is at the top of your page there. This is called Planck's constant. He was one of the people who came up with this idea. If you are a fan of the show Stranger Things, in one of the seasons, they have to get on the radio and get the sequence of numbers from somebody. This is the number that she holds hostage for a song as Planck's constant. So that's a little tidbit in trivia there. What does the N stand for? The N stands for how many photons are there. So for us, we're always going to be thinking about one photon at a time. So we're just going to leave N out of it. We're just going to say 1 for that. All right, so H is 6.626 times 10 to the negative 34. Is that a really big number or a really small number? Very, very small number, because we got 10 to the negative 34. All right. The joules is going to give us the energy. The seconds is going to cancel out with the frequency. All right. This is doing an animation that I wasn't expecting it to, so I'm just going to go on to the next slide. All right, so let's do a calculation. What is the energy of a photon of light from a red laser pointer? So remember, we said the red laser pointer had the wavelength of 650 nanometers, and the frequency we calculated was 4.6 times 10 to the 14th hertz. Okay. Which of those numbers do we need? E equals h nu. Which one are we going to use? The 4.6, right? Okay. So we're going to take h, which you have at the top of your paper. That's the 6.626 times 10 to the negative 34. And then you're going to multiply it by the 4.6 times 10 to the 14th. Now, 10 to the negative 34 is a lot more negative than 10 to the 14th is positive. So we're going to end up with something that's in the ballpark of 10 to the negative 20. Should be around 10 to the negative 19. So try that out, see what you get. And if you were getting something that is 10 to the negative 19, you probably have that. Now, if you are doing the well, you're obviously doing this on a calculator. Your calculator isn't going to type out 10 to the 19th. It's going to have a number, and then it's going to have up in the corner the exponent on 10 to this. So it's going to look like it's going to say that number to the power of this, but what it really means is this number times 10 to this. All right, so I get 3 times 10 to the negative 19th. Is that what you get? Okay, so again, on your calculator, that would look like, I mean, probably a bunch of numbers after 3, and then it would say negative 19 up in the corner. Okay, so this is something you have to know for your quizzes and your tests, that when your calculator says that, it's not saying take 3 and raise it to the power of negative 19. It means 3 times 10 to the negative 19. All right. Now let's talk about microwaves. Suppose I want to find the wavelength of a microwave coming from my appliance, meaning my microwave. Most microwaves run at a frequency of 2.45 gigahertz. So what is 2.45 gigahertz equal to? So giga is one of our modifiers that makes things bigger. So kilo is 1,000, mega is 1,000,000, giga is 1 billion. So which one of those do we think it is? C, yeah. So it's a frequency, so hertz means per second, so that's gets rid of B, and a billion is times 10 to the ninth. I'm not going to give you giga or mega, but you should know milli and you should know kilo. Okay, so now we know what number we're plugging in. We've got a couple of equations we've looked at. We are trying to find the we have the frequency and we want to find the wavelength. So which one is going to get me from frequency to wavelength? So we have to think about which symbols we use for which. Is D going to be helpful here? No. Okay. So we've used both the energy one and C equals, but C equals is the one that has the wavelength, lambda in it. So that's the one we're going to use. All right, and so here I've shortened C to 3.00. That's because I know that I only have 3 sig figs. So that's just rounding this to 3 sig figs. But you can use the 4 sig figs if you want. We'll just have to round it at the end. Oops. Apparently I didn't put the answer on that page. All right, so this time, are we dealing with visible light? No. So our wavelength is not going to be in hundreds of nanometers. Okay. Remember we said that our wavelengths for microwaves is on the order of centimeters, but our units that we're going to get out of this are not centimeters, it's meters, right? Okay. So, how many meters did you get? Was it less than 1 meter? Hmm. All right. I'm giving you a chance to look at it again. Was it less than 1 meter? Should have been. Oh, they capitalized it. See, there's a capital lambda. Undo that. Is that what you got? So remember, you have to change the giga to times 10 to the ninth. Now remember that a meter is going to be 100 times a centimeter. So if I change this to centimeters, I need to divide by 100 or move the decimal place too. So this is about 12 centimeters. That should be. Right? I can't tell. Are you getting this?
So after you do like you divide the C by your 2.45 times 10 to the 9.
Mhm.
How do you you divide it by 100
to get centimeters.
to get centimeters.
Right, but remember, okay, so what you're gonna plug into your calculator, if you are just plugging it straight in, I would do, let's see, on that one, I would do 3.00 EE, and that is above the x to the -1. And then I would do 8. And then I would do divided by, and then I would do 2.45 EE 9. Okay, if I wanted to plug everything in just manually, I would do 3.00 times 10 and then use the caret button, 8. And then I would definitely use parentheses on the bottom, 2.45 times 10 caret 9. Do it like that. All right. So not if you actually did get that number. Okay. I couldn't tell from looking at you if you were just like, yes, we got it already, or if you were like, I have no idea what you're talking about. Okay, you got there. Okay, good. Okay. All right. So the second thing that we said was a problem was, oops. Come on. The photoelectric effect. So what is the photoelectric effect? Basically, it's based on the idea of how solar panels work. You get light energy coming in, you turn it into electricity. And if we think of light as being a wave, what we want are really intense waves. So a lot of waves coming at the light, and we want it to be a high amplitude. Okay. But what ends up happening is that if I have a really low amplitude, but I have ultraviolet light, that has enough energy to get the solar panel working. But that shouldn't be enough to get the solar panel working if light would be a wave. It should have to be a lot of waves, really intense light. It should have to be really bright light. The fact that I can use something that's a very high frequency tells me that that energy is tied to that frequency, and that I can get that I can think of light as an individual photon with a lot of energy hitting it. So think of this as the difference between throwing a lot of ping pong balls at, like kindergartners throwing ping pong balls trying to knock something over, versus a professional pitcher from a baseball league having a fastball and trying to knock something over. All you need is one good fastball that's really directly hit to knock that thing over. Versus the kindergartners with the ping pong balls. I mean, they could be throwing stuff at it all day, and if you got a heavy enough object, it's not going to work. Okay. So this is the idea on a lower level, is the light coming in, knocking the electrons out into the circuit. And then I don't need you to write this down because I won't ask you about it, but if light is a wave, the amount of energy depends on brightness, and we should expect bright lights to emit electricity, and dim lights should take a while to build up enough energy. In reality, we only need a high enough frequency, even if it's dim light, and it will work right away. All right. So that is the gist of how we know light is both a wave and a photon. So you're going to do calculations with that on active. And then on Monday, we're going to say, how do we use this to look at an atom and figure out what orbitals are? All right. And hopefully I will have your tests back as a week. Thank you, you two, for joining me online.
Thank you, Dr. Nutt.
You're welcome.